Okay, welcome back again, everybody. Today we're going to be doing section 13.2, which is all about derivatives and integrals of vector functions. Let me go ahead and pull up the slides, and we'll get started. Okay, more good news. This one is also relatively short. There's not a lot of content, but there is some really important content in this one, so I want to make sure to emphasize a few things. Here's the overview. We're going to start by talking about the derivative of a vector function. Then we're going to talk about a very important vector called the tangent vector, and we're going to derive the formula for that. We'll look at some differentiation rules, basically the rules that you have for derivatives. Then we'll talk about the definite Riemann integral of a vector function, and we'll finish up with some helpful Mathematica commands, a couple of which we'll use in more detail later on in the course in chapter 14. But let's start with the derivative. So here is the definition. The derivative of a vector function has a very, very familiar form. This should look like your best friend almost. So if you've got a vector function r, then r prime is defined as the limit of this difference quotient, right? The notation is the same as what you've seen back in Calc 1 and Calc 2. dr dt is the derivative of r with respect to t. We can call it r prime if we'd like when there's only one variable. Maybe I'll mention this now. You do want to get comfortable with Leibniz notation because when you're working with multiple variables, you have to specify what variable you are differentiating with respect to. And it's hard to do that with just a single prime notation, because what do you mean when you say r prime? Do you mean derivative with respect to x, y, t, z, a, b, q? Who knows? But to construct the derivative, the formula is basically the same as what you saw in the past. You look at the difference quotient, you take the limit as the denominator goes to 0, as the increment goes to 0, and as long as this limit exists, then you have the derivative of that vector function at that point or at that time t. So the setup is very cool. Just as with the derivative of a real valued function, what you do is you look at the secant vectors. So, do I say that right? Yeah, secant vectors. So when we compute the derivative of a vector function, we are still finding the slope. We're finding the slope of the tangent line to a curve, but now the slope is given as a vector, and it's the tangent vector, right? So pretend you've got 2 points on a curve. You can describe this secant vector from P to Q. And what we're going to do is we're going to parameterize it with T, and then we're going to let H be our increment. So basically, we're going to let P be at the point R. I'm sorry, how do I say this? Yeah, so this is R of T. And this is R of T plus H. So a little bit farther along the curve, right? And that's where we get this difference of vectors right here. So the vector that goes here from P to Q is R of T plus H minus R of T. Just like before when you were looking at secant vectors back in Calc 1. So this is what's called a secant vector, right? Now do the same thing as before. You take the limit as H goes to 0, and then what happens is these secant vectors start to approach the tangent vector. They start to approach the tangent vector, and as long as this limit exists, then you actually do get a formula for the tangent vector itself at the point P. All right. Also have to make sure that it's not equal to the 0 vector. And then how do we define the tangent line? Well, the tangent line to the curve C at the point P is the line that contains the point P and has the same direction as the tangent vector. So do I say this in the next slide? I don't say it yet. The way that I like to think about it, again, is intuitively, right? The tangent vector is basically saying where the curve is going at an instant. And if you took me for like trigonometry or pre-calculus, I kind of mentioned this when we talk about circular motion. And the way that I describe the tangent vector is if, imagine a child is like spinning around a rock on the end of a string. Well, if that rock were to suddenly fly off, what direction would it head if it flew off of that circular path, right? It'll fly off in the direction of the tangent vector. So that's what the tangent vector is. Another one example that I like a lot, which we will see on the activity, I don't know if it's this one of the activities is imagine you were in a spaceship, right? Imagine you're in a spaceship and maybe you could say you're orbiting a star, maybe a black hole or something like that, right? Well, if you suddenly cut the engines, where is your spaceship going to go? Well, your spaceship is going to go in the direction of the tangent vector, and it's just going to coast. It's going to coast in that direction. So that's what the tangent vector is. It's like where things would go if you just let them off the hook. All right. Now that we've made sense of what the tangent vector is, basically the direction, right? There's another really important vector that we're going to explore in great detail in the next section, which is a bit longer. And this vector is called the unit tangent vector. Unit tangent vector. So if you remember back from, section 12.2, I think, one of the first couple sections, you can always find a unit vector in the direction of a given vector by simply dividing that vector by its length, right? And that's exactly what we're doing here. So if we want to find the unit tangent vector, we first find the tangent vector itself, r prime, and then we divide by the length of r prime. And we're going to need to use this a lot because, again, a lot of the times we don't want to have to carry around extra scalar baggage. We just want to know direction. So the point of this vector is that it basically tells us the direction that we're heading, and it doesn't incorporate any scaling of the vector. It's just the scalar is 1, right? So it's a unit vector in the direction of the tangent vector, which is really handy for us to use. All right. Now, naturally, we have the following theorem. So this is where things get nice. Now that we have the construction is similar to what we saw in the past. We have this. If your vector function is given in terms of these component functions, f, g, and h, then, and those functions are differentiable, if f, g, and h are differentiable functions, then the derivative of the vector function is merely the derivative, or is merely determined component-wise. You do the derivatives of the individual component functions, and this gives you the derivative vector. That's what it is, the tangent vector, right? So again, you have this similar idea of just doing things component-wise. What is r? R looks like this. What is r prime? Differentiate each of the components. That's r prime. That's the idea. So it's a nice result. Okay, this one I want you all to try on your own at home. Not too hard, just a straightforward example. Maybe it'll kind of get those differentiation juices flowing again. But here's a vector function r, and I want you to try to find the derivative first of all. So find the tangent vector. And then I want you to find the unit tangent vector at the point where t equals 0. So mull that over for a minute, let that marinate in your brain. And then since this is the first example, say something out loud about how you're going to start. Remember, you don't have to be talking to anybody. It's always nice when you are, but you can talk to yourself, you can talk to your neighbor, you can talk to your peer, whoever. Just say something out loud. Right, and now try to compute it. Find the derivative of r, and then find a unit vector in the direction of r prime. All right, here we go. So this should feel very familiar, hopefully, and kind of comfortable, right? One of the nice things about Calculus 3 is there's a lot of comfortable content where it's like, oh yeah, I can do derivatives, I can handle this. Compute the derivative of this component, compute the derivative of this component, chain rule, compute the derivative of this component, chain rule again, and then we're going to get this. So this is r prime. This is giving us the tangent vector. So maybe just to elaborate a little bit, what you can think of is that this function here, this r prime function, that is telling you the direction the curve is facing at every value of t. So it's literally like where you are pointing at every possible value of t. Now, if we want to find a unit vector in that direction, we need to find the length of this vector here, the length of the tangent vector. So we use the length formula, the distance formula, essentially. The good news is this: it only asked us to find the unit tangent vector at a point, and that's just going to save us a little bit of a grossness in terms of calculations. We know that r prime of 0 is given by this vector right here. So if we want to know what t of 0 is, that's the unit vector at that moment in time. We're just going to divide r prime by the length of r prime at this point. At this point, t equals 0. And this is about as simple as it gets. About as simple as it gets. Fair warning, sometimes your calculations are going to get very messy in this course, partially because it's kind of like you're doing the same thing that you did back in Calc 1, excuse me, and Calc 2, but now you got to do it 3 times. And it doesn't always simplify to something nice. So for example, there really is no nice way to simplify this radical. It's just a messy radical, and we just got to kind of live with it. All right. Yes, okay, so here's a fun one. This is a good one I want you to try at home as well. See if you can find the parametric equations for the tangent line that is tangent to the elliptical helix given by these parametric equations at this point. All right, so this one, think about it for a minute. Give yourself some time to process it. Right? Now say anything out loud to yourself about how you might find the tangent line. All right. Okay, and now try to work it out on your own. You're finding the equation of the tangent line. So remember, you're not just finding the tangent vector. You're not finding just the slope. You're trying to find the equation of the line itself. All right, here we go. So first thing, finding r prime or finding the tangent vector isn't too bad. Just differentiate each one of these functions, and you've got a formula for the tangent vector. So let's start with that. There's our r prime. Now what we're going to do is, because we are looking for the equation of the tangent line at this point, we're going to plug in well, we got to figure out what the parameter is, and we're going to plug that into this just to get the slope of the tangent line at that point, or the direction numbers, you could say. So here we go. Looking at this point, we can tell by inspection that this occurs when t is equal to pi over 2. So one thing I want to point out about this example is we were not given the time or the t value, the parameter value, where we wanted to find the tangent. We were given the point in space. So we have to kind of backtrack and say, okay, well, if this is the point in space, what t value is associated with that point? Luckily for us, z of t is just the identity function. So right away we can see that t is going to be pi over 2. If that was not the case, then it can be a little more complicated. You just have to basically solve for t when you know what this point is. And then, you have 3 values, you'll have 3 equations, you can find that value of t. Okay, all right. So plugging pi over 2 into r prime gives us this vector right here. So this is the tangent vector at t equals pi over 2. This is what the vector looks like. So we've got a point, we have a direction, so we can describe the line, right? We can describe the vector equation of that line. So I'm going to write it like this. Wait, where did I? I'm not sure why I called it V. Not a big fan of that. Yeah, that's all right. Yeah, no, that's not all right. I don't like this. Don't call this V. V usually means velocity, so I want to be a little bit careful with that. Maybe for this one, I will call it A. There you go. So what is the vector equation of this line? Well, you remember you start at this point, this position vector, and you go this far in this direction. Putting it all together, we get this. So this is the vector equation of the tangent line. So this vector right here describes every point on the tangent line. Now we can peel off the parametric equations. X is negative 2t, y is 1, and then z is pi over 2 plus t. So these are the parametric equations for the tangent line itself. All right. Okay, next, good stuff. Naturally, the second derivative is exactly what you would expect. Just take the first derivative and differentiate it again with respect to t. So it's r prime of t prime, which gives you r double prime of t. Using Leibniz notation, it's literally just differentiating the derivative with respect to t again, and you get d squared r over dt squared. Pretty nice, huh? Okay, so second derivatives are what you would expect, third derivatives, fourth derivatives, nth derivatives, and so on. Those are about the same. Now, some important differentiation rules. We get everyone's favorite, which is linearity of the differentiation operator. This gets used all the time. Basically, if you want to differentiate a sum or a difference of vectors, you can just differentiate the individual vectors and then add or subtract. Furthermore, if you wanted to differentiate a scalar multiple of a vector, you can just pull the scalar out and differentiate the vector and then multiply by the scalar. So all that stuff that you did back in Calc 1 where you would pull out constants and you would throw the limit operator over sums and differences, that is still all good. You can still do that. Some other nice properties, we get this theorem. Suppose that u and v are vector functions and f is a real valued function. So take note that f is a real valued function here. And let's take a look at all these interesting results. So if we take this vector value, or sorry, if we take this scalar valued function or real valued function and multiply it by this vector valued function, and then we do the derivative, guess what? You get the good old product rule. So the product rule holds in this case. We're going to look at several product rules here. So f prime u plus f u prime, that's the good old product rule. Same structure, right? What's even cuter is this. You get the same structure for the dot product. So if you do u dot v and you want to differentiate a dot product, you use the product rule. U prime v plus u v prime. Hooray! Works out nicely. And it even works for the cross product. So if you have u cross v, then the derivative of u cross v is u cross v plus, u prime v plus u v prime, except now it's a cross. So the good news is the product rule works the same as you would want it to, no matter if you're multiplying by a scalar function, or you're using a dot product, or you're using a cross product, the product rule still applies, which is nice. Another nice thing, this one, everyone's favorite. And remember, if you took me for Calc 1, you got to know the chain rule. You really, really got to know the chain rule. You got to make sense of the chain rule. We're going to see it in a very big way, in a more generalized way later in the course. And for those of you that go on to take things like differential equations and even beyond those courses, you're going to need to know that section, 15.9. But if we compose the vector function with a scalar function f, then the chain rule applies exactly the way that it did back in Calc 1. What is the derivative of u of f of t? It's u prime of f times f prime. So derivative of the outer function with the inner function left alone times the derivative of the inner function. And that's how it works. So these are great, right? These are great because this basically means you don't really need to learn anything new. You just got to remember what you learned from Calc 1, except now we have different objects playing together and we have different types of products, right? We have a scalar product, or I shouldn't say that. We have a scalar multiple, we have a dot product, we have a cross product, composition with a scalar function, that kind of stuff. All right, we're going to prove a couple of these, although, you know what, I should say this. Okay, we're going to do this. Which one do we prove? Yeah. Okay, this is actually a proof that I want you to try on your own. So I'm going to throw up the thinker for a minute, and I want you to try to prove this one. So try to prove the product rule for the dot product. You try to do this one on your own, okay? Just take a couple minutes, try to work it out. How do you think you're going to start? Right, now write it out. So try to write out your proof. And remember, you're proving an identity here. So basically you want to start on one side and arrive at the other side. Don't start on both sides and manipulate it and get 1 equals 1. That's not a valid form of proof. All right, let's do this one together. Perhaps unsurprisingly, the way you're going to do this is you're going to rely on the components, and you're going to do this component-wise. We're going to do this in V3, so we'll just keep it easy for V3. For those of you that go on to take a real analysis course, you would actually prove this in generality for Vn, but we'll just stick to V3. Maybe I should have said that earlier. So here's what we're going to do. We're going to let u equal f1, f2, F1, F2, F3. we're going to let V equal G1, G2, G3. Then just by the definition of the dot product, this is the dot product. And now because the derivative is linear, or the differentiation operator is linear, we can, if you want to differentiate this, we can throw the differentiation operator to each term. And then we can use the product rule on each one of these, the good old product rule from back in Calc 1. These are just scalar functions, right? Real valued functions. And here's the computation. Derivative of this is the derivative of this. Linearity plus the product rule gives you this. Now you can move things around a little bit. So shift things around. Let's see, this and then this gives you this. And then the rest. But then if you kind of like look at squint your eyes a little bit and just look at the pieces, this is actually just the dot product of U. Where is it? Right there's the cut of U and, or sorry, U prime and V. And then U and V prime. So U prime V plus UV prime. And that's the proof. Cool stuff, huh? Right. Oh yes, okay, so now we have this, this important example. We're gonna see this example more later on, so it's good to make sense of it. What we're gonna do is we're gonna show that if the length of a vector function is a constant, meaning that the length does not change, then that means that the derivative r prime has to be orthogonal to the original function for all t. So if the magnitude of a vector function is constant for all t, then the derivative is orthogonal to the original function or vice versa, right? So this is one where I just want you to think about it for a minute. We're going to do it together. You don't have to prove this yourself, but think about what this says for just a minute. Okay, now just say this out loud to yourself. Try to rephrase it in your own words, like verbalize it yourself. Okay. All right, and now let's prove this one together. So let's think about what we're going to prove first. So we need to show this. We need to show that if the length of this vector function is always constant, then the function is always orthogonal to its derivative. Remember back when we learned about the dot product, if you want to show something is orthogonal to something else, or if two vectors are orthogonal, then you got to use the dot product. So really what we need to show is this. We need to prove that r dot r prime is equal to 0. That's the goal. Now, what we're starting with is that this length is constant. So the length of RT is just equal to C for some constant. And if you remember from properties of the dot product, what this means is we can square both sides, but the length of a vector squared is just equal to the dot product of the vector and itself. So this is one of those properties of the dot product back from section 12.3, right? So currently we have this equals this. Now what we're going to do is we're going to use one of those properties of the differentiation operator that we just saw a minute ago. We're going to differentiate both sides of this equation. The derivative of a constant is just 0. And then here we're going to use the product rule, right? The product rule occurring with the dot product. So r prime r plus r prime. But remember the dot product is actually commutative, so we can commute these. We can move this here and this here. And then what we end up with is 2 times r prime dot r. Divide both sides by 2. 2's cancel, and you get, voila, exactly what we needed to show, which is that r prime dot r is equal to 0. There we go. So we proved it. This means that if this is true, then this dot product has to be 0. But this dot product being 0 means that r prime is orthogonal to r for all t. All right, that's what's going on. Now, what's the intuition behind this? What's the geometry behind this? Well, keep this in mind. If the length of that vector is always constant, that means that it basically is kind of like doing this. It's literally like this pencil, right? The pencil is not extending or shrinking in size. So no matter where the tip of the pencil is pointing, it's never changing length, right? Well, if that's the case, then that means that whatever the curve looks like, it has to lie on a sphere. It has to lie on this sphere right here of radius c. So here's r of t, right? Just like that. So ponder this again for just a minute. Maybe I should throw the thinker up there. There you go. So what I'm saying is, if the length of the vector never changes, and you've got this vector function describing where you are at any given time, well, that just means you're moving around a sphere, right? There you go. We're just moving, it's just moving around a sphere. So if you're if you're on a sphere, think about how you could make a tangent to a sphere. You're always going to be pointing like this. And so because of that, the original vector and its derivative are always orthogonal. That's the idea. Okay, go back to this. Yeah, and we will see that again throughout the course, so it's a good thing to keep in mind. If the length is constant, then the position vector is always orthogonal to its derivative. Okay, now we've done derivatives, let's move on to integrals. And don't cringe, this is actually very gentle, very natural. Basically, if you want to do the derivative of a vector function, you do the, if you want to do the integral of a vector function, you do the integrals of the components. We're going to get into much, much more interesting integration in chapter 16. That's when we start doing vector calculus. That's where things get really cool. For now, this is just, again, doing what you did in Calc 2 3 times over. So you can groan over that. You can groan over that. If you want to do this integral, you're going to be doing 3 different integrals. So this is where you cross your fingers that the integrals are easy. And this is also where you appreciate the Weierstrass approximation theorem. And if you've got some funky function, as long as it's continuous, you could just use a polynomial and carry a little bit of error with you, and that can make life a little bit easier. So definition here: if your vector function is given by these component functions, and you want to do the integral, the definite integral from a to b of r of t, then do the definite integral of each one of those component functions, as long as they are integrable themselves. Yeah, if one of these functions is not integrable, then you obviously could not compute the integral of the vector function that has those as components. All right, here's something that's very beautiful that follows from this. The fundamental theorem of calculus part 2, back from the end of Calc 1, extends very nicely and very simply. So the fundamental theorem part 2 also holds. The definite integral of r of t is equal to r of b minus r of a, where capital R is an antiderivative of little r. So that still holds. How cool is that? Right? Oh yes, so some notes about this. One thing I want to point out is notice that the integral of a vector results in another vector. All right, so we're still in the realm of vectors here. If you integrate a vector, you end up with a vector as a result. If we let r prime be equal to v, so in other words, if you think of r prime as a velocity and just relabel it with a v, we can think of v as velocity and r as position. There you go. Now, if you integrate the velocity vector, this is where you're basically applying FTC1, right? So if you integrate a derivative, you recover the original function. In this case, because this is indefinite, we need that plus c. So hopefully your instructor or your professor emphasized that you got to include the plus c when you have an indefinite integral, because there's a whole family of possibilities that could result, a whole family of antiderivatives. But this is essentially FTC1 for indefinite integrals. Cool stuff. Okay, all right. Oh, I should have let you do this one. Wait, pretend you can't see any of this. Try to do this one on your own. Ignore this. There you can't see any of it. All right, compute the integral of that vector function. I guess I'll just throw the writer up right away so you can get started. There's the vector function. Do the integral. Find the integral of it. Okay. All right, now we'll do this one together. You're just going to integrate component-wise. So you're going to do integral of 2 cosine t plus, times I plus integral of sine t times I plus integral of 2t times k. Oh, sorry, I meant times j back here. There you go, 3 individual integrals. Luckily, these are straightforward integrals. Doesn't take that long to do them. So you get this. And just remember to compute the plus c. So that rule is still the same. If you've got an indefinite integral, you got to include a plus c. If you've got a definite integral, you technically could include the plus c, but it's going to get washed out when you apply FTC2 because you'll get c minus c, which is 0. All right. Okay. Now, nearing the end here, let's talk about some helpful Mathematica commands, and these can really come in to save you later and just to save you some time. Naturally, or I'll say this, differentiation and integration, they're fundamental operations. They're fundamental mathematical operations, so naturally Mathematica has commands for each. So the command for differentiation is simply D, capital D. I'll talk about the rest of this in a minute. So if any of you took me for Calc 1, you might remember that I introduced this notation way back then in Calc 1. And I was like, here's like 7 different ways of writing the derivative. This is why, because now this is the symbol that gets used a lot when you end up with multiple variables. Because differentiation is an operation. It's just D, right? It's D. So this is, oops, there you go. So that is the command. You can also call this command by doing escape PD escape. The reason that it's PD is because it will give you a partial derivative, and we're going to talk about those in chapter 14. So you can type escape PD escape, and then you can use control underscore to indicate which variable you are differentiating with respect to. I'll show you that in just a minute here. And we will revisit this command in later sections when we start talking about partial derivatives. Right now, we don't have partial derivatives. We're just differentiating with respect to t. That's it. The command for integration is integrate. So you can use that command and just type integrate, enter your function. It could be a single scalar function. It could be a vector function. Or, yeah, there's that. So it's integrate. If you want something that's a little more shorthand for that, you can do escape, int escape, and then escape dd for the differential symbol, the d at the end. And again, we will revisit these commands later as well when we're doing partial derivatives more. But let's go to Mathematica, and let's take a look at it here. All right, see this? Yes, okay. So here's an example. Which one? Oh yeah, let me do this real quick. Let me go back to that example we did earlier in the lecture. Where are you? Is it this one? No, it was earlier on. It was, where are you? This one? Yeah, this one. Okay, so I'm going to flash back to the slides for just a moment here. We did this example earlier on, and you had to find the derivative of it at a point t equals 0. So you compute the general derivative of it, and then you plugged in that number, right? So now let me go back to Mathematica. What I've got here is, maybe I can zoom in a tiny bit more. That's a little better. Okay, so here I've got D. So D is just the differentiation command. And then look, what I was able to do is I was able to enter my vector function as a list, just like we've seen before in Mathematica, entering vectors as a list. So here's the first component function. Here's the second component function. Mathematica uses capital EXP to represent the exponential function. So this is one of the reasons why I like this particular version of the book, because they talk about the exponential function, and very commonly exp is used as the exponential function. So sine of exp of t, and then log. This is another thing that, again, if you took me before, I mentioned that once you get beyond a certain point, log really means the natural log. And so like if you took me for pre-calc or calc 2 or calc 1, log is the is the natural log. Log is the natural log. And so we tend to use this symbol just to represent the natural log. If you wanted to talk about log base 10, then there's another command for that. I think it's actually log 10. Yeah, it's literally log 10. So if you want to do log base 10, then you indicate it by doing base 10. So what I'm trying to say, to summarize, is that this is natural log. That's all. All right. So I'm going to do derivative of this vector. I have to indicate what I'm differentiating with respect to, right? There's no, how do you know what you're differentiating with respect to? You got to tell the computer. So I'm differentiating with respect to t, and this is what it gives me. There it is. Oh, remember you can enter, see these fancy e's? That's just the exponential function. You can enter it just by doing escape exp. Oh no, it's EE, right? Yeah, EE, escape. That's how you get the exponential. Or you can just type exp. But that was the derivative we computed. So let's go back to the slides actually and see if it agrees. Yep, sure does. Let me lift this up. There it is. There you go. Back to Mathematica. There it is. So what I'm saying is Mathematica can do derivatives for you. That's all you got to do. Just do d and then whatever you want to differentiate. Okay, what I've got down here is me using that Ph.D notation. So what I'm going to do is this actually. I'm going to delete this for a sec. I've got my vector function right here. And instead of doing d, I'm going to type escape Pd escape, and it gives me this little symbol here. This is the partial derivative symbol, the partial derivative symbol. We'll explore this much more later on. Now what I need to do is I need to hit control underscore, and it makes this little block down here. And that little block is where you're going to write t, because we have to tell it what we're differentiating with respect to. And then we can do shift return, and we get the same result. So here's two different ways of entering a partial derivative. Not too bad. Now let's go down here to integrate. Integrate. So same thing. This one, what was the example? Oops. What was the example? The one that I forgot to erase, I believe, or forgot to hide. Yeah, this is the one. Let me flash back to the slides for just a minute. So remember we did this example a second ago, and this was the result we got for the derivative. I'm sorry, for the integral. Well, we're going to do it with Mathematica now. So Mathematica, integrate this vector function with respect to t, shift return, and it's exactly what we got. One little note I'll make is that this is they're letting c be 0 here, so this is like the antiderivative you get when c is 0, but you can see that it's still giving you the formula for the antiderivative. That's the important part. There it is. This is me just showing that you can also use escape int escape and then escape dd for this. So I'm going to do that as well, just to show you what it looks like. So I'm going to hit escape int escape. Gives me the integral sign. Over here, remember, you got to include the differential. So hopefully your professor harped on you about that in Calc 2. You have to include the differential and Calc 1. So I'm going to do escape dd escape, and I get a differential symbol. And I'm going to say t. So now I'm just telling it I'm differentiating with respect to t again, and shift return, boom, same result. So Mathematica can differentiate and integrate things for you. It's a good way to check your work. So try to do it by hand, and then go to Mathematica and have it verify, and then hopefully you got the same thing. If you didn't, then you probably made a mistake. Okay. So let's go back. I think that is it. Let me double check. Yeah, that's it. So on that note, let's play. We're going to do an activity related to this. A lot of cool commands, a lot of straightforward stuff. So I hope this was a gentle section. If you've got questions, remember to ask them in class. But other than that, I'll go ahead and say goodbye, and I will see you all again next time.